our honor, pleasure to host Professor Abdullah ALAMER from the University of King Faisal. And we are here as part of the research methods SIG of the IAPL. Bianca is our coordinator, and El Maki, Alfef, and myself are co-coordinators of this SIG of the IAPL. So today we have Professor Abdullah ALAMER, who will talk about structural equation modeling. The title of his presentation is Why Structural Equation Modeling is Very Appealing for Researchers. As I flagged before, Professor Abdullah ALAMER is an associate professor in the psychology of language learning at King Faisal University. He holds a PhD from the University of New South Wales, Sydney, Australia, where connecting today, although I'm in Melbourne, not in Sydney. Using advanced statistical methods, Abdullah's main interest lies in research on the psychology of language learning. A dominant method used in his work is structural equation modeling. Abdullah's research appeared in top journals, including Applied Linguistics, Studies in Second Language Acquisition, Language Teaching Research, System and Computer-Assisted Language Learning. He co-authored papers in SEM with top statisticians such as Joe Hare, Herb Marsh, and Yor Hensler. So it's my great pleasure to give you the floor, Professor Abdullah ALAMER, and thank you again for accepting our invitation.
Thank you so much. By the way, I did my master in Melbourne, Monash University, so we have something in common.
Yeah, we do. I can see.
Yeah. Okay, so that's explained the chemics between the team with the SIG research methods. So I'm sharing my screen. Okay. Okay, can you see the
Yes, we can.
the slides?
Yeah, it's perfect.
Fantastic. Okay. Hello, everyone. My name is Abdullah ALAMER, and when some friends forget my name at a conference, they say, I know you, I know you. You are the SEM guy. So I'm okay with that, actually. It's better than not recognizing me entirely. So if you forget my name. So it's okay to say, yeah, you are the one who works with structured equation modeling. That's totally fine. Yeah, I would like to thank the International Association for the Psychology of Language Learning, especially the Research Methods SIG, for inviting me to speak on such an exciting topic. You're either so excited or worried, but I promise to make it as simple as possible. A special thanks to El Maki Amri for communicating with me and arranging everything so thoughtfully. Thank you, everyone, for this lovely event. So, okay, in today's talk, I want to highlight several aspects of SEM, focusing on its beauty and usefulness. I'm happy to indicate that our field has increasingly endorsed exciting applications of SEM over the last decade. More appropriate implementations of SEM have started to emerge in recent years, thanks to open-minded researchers, I guess, who are willing to learn, adapt the method. Also, more user-friendly and free software packages have emerged during the last decade, making SEM readily available. So before moving to the topics of today's talk, I would like to mention something critical. We should not seek an answer to a question like, which is better, quantitative or qualitative? I know we are research method SIG, so let's talk about this. I believe each method answers specific types of questions. As such, one should start with an intriguing research question, and then find out the method that best answer it. Thus, some research questions are not suitable for SEM, and some are best answered by SEM. So we should have respect to the two methods as well as the hybrid mixed methods. So let's keep this balanced view in mind and explore the following topics. SEM as a method that accommodates latent and emergent variables, which was a hot topic, by the way, for our field in 2024. My team and I published at least 3 or 4 papers about emergent variables. So I want to highlight that. I will show something interesting. How can SEM perform basic analysis, actually? Analyses such as correlation, t-test, and multiple regression. Yes, it's true. SEM can indeed do that. Next, I will explain how SEM improves these basic analyses by using full latent emergent variables. Finally, depending on the time and audience preference, we can discuss how SEM can tackle complex relationships like mediation, moderation, and how SEM can answer exciting research questions like longitudinal trajectories. If you have questions along the road, please post them on the chat. I am following up. And I will try to respond to them depending on the context. If the question is strongly related to the slide, then I will try to respond and address that question immediately. But remember that we will have room for Q&A at the end, toward the end of the presentation. So let's jump in. Okay, I would like to share the story of how my journey with SEM began. That will give you a context. So during my PhD, my supervisor, Jian Lee, her name is included in my paper there, invited me to her office to discuss my PhD proposal. Okay. At that stage, my proposal was a mixed methods research design. She told me that she only worked with quantitative methods, specifically SEM. As she discussed her experiences and past studies in educational psychology using SEM, she turned around, pulled a book from her shelf, and placed it on a table between each of us. The book was enormous, thick. It's like an Oxford dictionary. My God, it was so thick. She said, "You should learn structural equation modeling, okay? This is the book I use." It was the M+ User Guide version 7, similar to the one showing in the slide. And she said, "Read this book every day. This is your Bible now." Well, I don't read Bible. I would read Quran since I am Muslim. But you get the idea. Read it every day. It's something that is now attached to you. She said that in a tone that was meant to be intimidating, assuming I had no experience with SEM or interest in it. But inside, I was actually thrilled. It was like being asked to ride a roller coaster by someone thinking you would be terrified. But couldn't wait to jump on. So anyways, I reached out the book to take it, but she said, "What do you want to do? What do you want to do?" I said, "I think I will take it home to read it." She replied, "Oh, this is my version. Okay, go get one for yourself." So on, my journey with SEM began. For my PhD, I used Amos, if you are familiar with that software. It was so popular back in 2014 due to its user-friendly interface and functionality. when I was preparing my model, actually, I was fascinated by the work of Lindy Woodrow, who happened to be a faculty member in the crosstown counterpart, the University of Sydney, the competitor to my university, UNSW. So her PhD thesis around 2006 happened to be a beautiful structural model. It actually inspired me a lot. It includes motivation, anxiety, learning strategies, all in one structural model. I contacted her actually to learn more about it. But she told me that she moved to the UK for retirement. So unlucky me, I guess. Okay, my PhD thesis was a large model actually, consisting of several factors, which was then published in System in 2019, and you can see the publication in the slide. So this is me, I guess, with ACM. Over the years, I have learned a great deal about ACM, and so far I published around 35 research papers, I guess, in top journals, all of which I've used ACM. I once thought there would be a point where I could fully understand the complexity and the functionality of ACM, but my goodness, this method keeps evolving every time. The fact that there is a dedicated journal to the applications and development of ACM is a clear indication of how rapidly this field is growing. Statistically speaking, there are 6 issues of this journal published every year. So it's around 15 articles in each issue, constituting around 90 articles annually, all dedicated to ACM applications. This is a big wow. So I always find myself busy learning something new, experimenting with the new ACM topics, and the drive to apply these advancements to empirical data is just so compelling. So I hope you can feel the excitement that I have. Well, one of the most exciting advancements, which I'm super happy about in applying ACM, is the availability of user-friendly software like Jamovi and JASP. These programs offer an intuitive drag-and-drop interface, making ACM extremely accessible, even for those with limited technical expertise. I like these 2 programs and find myself going back and forth between them. There are literally hundreds of tutorials, videos on YouTube, covering lots of aspects about these software packages. You can actually learn ACM fundamentals and advanced topics by exploring these videos. Something like path analysis, factor analysis, mediation, moderation, and so on. The great news is that both programs, JASP and Jamovi, receive regular updates, continuously expanding their capabilities over time. So why not give them a try? A simple search can get you started. At a personal level, I suggested several functionalities to be added to these 2 software packages, Jamovi and JASP. And I'm super happy to see that the developers listen to feedback. They implemented most of the suggestions I made to them, which is extremely helpful. So you can even go to their website, suggest some either report bugs or features. So, okay, let's jump in, start immediately with this. I know this slide looks a bit detailed, but it is very important to start with. Let me explain the 2 types of constructs that ACM deals with. This is really important. Latent variables and emergent variables. These are fundamental and foundation concept in SEM. And understanding their differences is crucial. I think before 2022, there were hardly any discussion in our field, language learning, about emergent variables or composites. So we were exclusively thinking about latent variables, which is on the right. So first, latent variables, also referred to as common factors, are constructs that are represented by items that are similar in meaning. For example, when measuring a concept like academic motivation, you might use several survey items that all point to the same underlying data. These latent variables are modeled as unobserved factors that explain the relationship among the observed variables. Techniques like exploratory factor analysis, EFA, confirmatory factor analysis, CFA, and even the new one, exploratory structural equation modeling, ACM, are commonly used to analyze latent variables, okay? On the other hand, we have the new one, the new member of the family, emergent variables. Let's welcome them. Also known as composites. Composites are formed by combining items that are distinct in meaning. Distinct in meaning. So these variables emerge from the collective contribution of their elements, and each item carries its unique information. For instance, when creating an index or composite score for something like socioeconomic status, so we have the elements like income, education, occupation. These are distinct, but together combine to form the overall construct. A method like confirmatory composite analysis, CCA, is often used for these variables to assess them. So to summarize, latent variables focus on underlying commonalities, while emergent variables focuses on the meaningful contribution of distinct items. I will give more examples in the next slide. So let's now consider that structural equation modeling deals with two types of constructs, okay? Together, we are talking about SEM, whether composite or common factor. So this slide illustrates how the items in a latent variable or common factor look. Here, the construct being measured is second language intrinsic motivation, which represents the internal drive to learn a second language for enjoyment and deep interest. I like to think of a latent variable as a set of balloons. Each balloon or item represents a similar part that other parts or balloons represent. So they are very similar. In this example, the items of second language intrinsic motivation could be these four. Learning a second language is fun. Attending second language classes is enjoyable. Learning a second language is interesting. I want to learn more about the second language. So these four variables, I think we can agree that they are similar in meaning. So what is interesting here is that their items are similar. So if one item, such as item 4, is dropped or removed, the overall meaning of the constructs remains intact. Just like removing one balloon from the group, a set of balloons still there. Okay, I hope this is clear to you. So it's like just removing one balloon, we still have a group of balloons. Removing item 4 means that we still have a group of items represent intrinsic motivation. So this highlights the core understanding of latent variables as they capture the shared variance among the items rather than relying on any single one. Any question about that on the chat? I will follow the chat. If there is any question about this, just please post and I will try to follow. So yeah, dropping item 4 doesn't affect the overall meaning of the construct. This is really essential. Let's go to the emergent variable. Let's look at this construct called emergent variable, also called composite. In this example, we are examining a construct called cognitive strategies, which is formed by combining distinct but related elements. Each item here represents a unique strategy for learning English. Let's see. I try to find patterns, grammar in English. I find the meaning of an English word by dividing it into parts. I use new English words in a sentence so I can remember them. I try not to translate word for word. These items are not interchangeable, right? And they each contribute uniquely to the overall construct. To help conceptualize this, think of a car. A car is made up of many distinct parts, right? Like the engine, tires, seats. Each part serves a specific function, and together they form the car. However, if you remove one critical part, like the engine, the car no longer functions as intended. Similarly, in an emergent variable, removing an item like item 4, in this case, I try not to translate word for word, does indeed affect the overall meaning of the construct. So we are losing a critical aspect of that construct, because every item here plays a unique role in forming the composite of the emergent variable. This is a key difference from latent variables, where the items are interchangeable there, as we discussed. Here, the construct emerges as a combination of its unique components. So understanding composites or emergent variables is a new thing in our field. Actually, the first time we mentioned this was in 2022. So we are talking about 3 years or 2 years. Okay. So, but SEM can do basic analysis perfectly. So let's jump to another aspect. Yes, it can be surprising for many that SEM, although it's complex and advanced, can indeed do first generation analysis like correlation, regression, t-test, and ANOVA. Yes, SEM actually builds on these analyses and expand on them. So this is critical to understand. SEM, if applied that way, will produce almost identical results. Knowing this should refute the claim made by some reviewers, some even editors, that SEM is only for large sample sizes. No, this is not true. If you can exactly replicate t-test or correlation, then in this case, SEM requires same sample size. But to be clear, SEM is actually developed to handle complex tasks, okay? But it still can do basic analysis. So let's showcase how SEM can be used for first generation analysis, okay? Let's have an example. This is a lovely example, an easy one. So this slide showcases how SEM can be applied for correlation through basic methods and SEM. On the left, we see an example of a correlation matrix from traditional software like SPSS. Here, the correlation coefficient between VLT, or the vocabulary level test. VLT refers to vocabulary level test time 1 and vocabulary level test time 2, which refer to vocabulary level test is 0.67, which is statistically significant in this case. On the right, We have the same correlation modeled using SEM in software like Jamovi, Amos, whatever. The value is the same. It is 0.67. So SEM can provide almost identical results. In the pictures below, you can see the tabs that lead you to correlation and SEM in Jamovi. If you wonder how to get to these two, you can tab analyses and then go to regression correlation matrix. For SEM, you click analyses, SEM, and then SEM interactive. I know we cannot go or delve into the software itself, but this is just a small indication. So what are you recommending for determining an adequate sample size for SEM, especially when working with small or hard to read? Okay, this is a really tough question, Maki. So let's move this toward the end, but this is a really good question. I know many people would like to ask about this. Okay. Here is the linear regression. So this slide demonstrates how SEM can be used against or comparable to multiple regression analysis. On the left, we have a traditional multiple regression analysis from SPSS. The model predicts vocabulary level test time 3 using 2 predictors, VLT time 1, VLT time 2. The standardized regression coefficients are 0.16 and 0.76. Both statistically significant. The R-square value is 0.78, indicate that 80 or 78% of the variance in vocabulary level time 3 is explained by the predictors. This is multiple regression. On the right, we see the same model represented using SEM in Jamovi. The path diagram provides a visual representation of the relationship between the variables. So results obtained through SEM closely resemble those from multiple regression analysis. This is really interesting, right? Yeah, adjusted, I think. I think the normal one, not the adjusted. I think, Michael. But you can always request that in both software, in both cases. So SEM can also be used as an alternative to traditional t-test, even t-test, and ANOVA. On the left, we see the results from traditional independent sample t-test conducted in SPSS. The t statistic is 3.45, with a mean difference of 5 between the two groups. The grouping variable referred to as con1 xp2 on the diagram on the right. This result is statistically significant with a p-value less than 0.005 or 1. On the right, we see the same analysis conducted using SEM in Jamovi. The relationship between the independent variable and the dependent variable is represented by a path in the model. So you estimate the path from grouping variable to the outcome. The mean difference is shown as -5, which matches the t-test result. And the z value in SEM is 3.47, nearly identical to the t statistic in the t-test, confirming that SEM reproduces almost identical results. Is it the case that each program is business work like a magic box? We feed the information. Not sure. I got a question through direct message. It depends on the data. Usually the statistics or the analyses, whether being conducted in Jamovi, SPSS, SAS, or whatever, should provide the same result. This is my understanding. Okay. So let's have the first remark here. SEM can do and should generate almost identical result to first generation analysis. So if you have the same setup for correlation being conducted in SEM, you should get the same result. In such cases, ACM requires same sample size. No one should say, okay, because you are doing this in ACM, your sample size needs to be 300 or 200 or whatever. And let's go back to correlation as it requires 50, 70, or whatever, depending on the guidelines you are following. No, if you are using ACM for that particular analysis, then it should matches the same guideline. Model fit indices in these cases for correlation multiple regression are irrelevant. Why, you are wondering? Because these models, multiple regression, ANOVA, t-test, are saturated, meaning that all relationships possible are estimated. So there is no degree of freedom. We are estimating everything in the model. So no model fit indices will be produced for these analyses. Interesting, right? But what ACM can add then? Actually, what can ACM add to traditional first generation analysis? I know that most of us would not come to ACM to replicate first generation analysis, but let's find out the advantages. ACM effectively handles data. This is a tremendous advantage over first generation analysis. It employs a method called full information maximum likelihood, FIML. Keep this in mind. This is a fantastic and unbiased method to handle missing data. Using all available data without resorting to problematic methods like list-wise deletion, which is sometimes the default in SPSS. This results in more robust and accurate analysis, even when some data points are missing. Like when you collect data from time 1, time 2, time 3, usually you are likely to lose data over time. If IML, the full information maximum likelihood, is a fantastic method that handle such cases. 2, ACM deals with non-normality with ease. I think this is a very underestimated or even wrongly claimed aspect of ACM. I read a lot about the idea that ACM requires the data to be normally distributed, especially in old literature. When I say old literature, I'm referring to literature before 2010. Okay, so this is true in the past, like 2010, but now it's the best statistical method, in my opinion, to handle normality. You have 2 options. For continuous non-normal data, such as Likert scale responses, strongly disagree to strongly agree. I know there is a debate whether this should be treated as continuous, but for my opinion, in my opinion, they can be treated as continuous, especially if they are 5 responses and more. Okay, so if you have 5 responses, possibly 7, then they can be treated as continuous. In this case, if you have non-normal data, you can use maximum likelihood with robust standard errors, referred to as MLR. This is a fantastic estimation method. Unfortunately, it is not implemented in AMOS. It is implemented, I think, in almost all remaining software packages for ACM because it handles the non-normality, including Jamovi. It handles this, or actually provide this option, MLR. For binary or categorical data, such as yes/no responses, ACM can use WLSMV, refers to weighted least squares, mean and variance adjusted. So ensuring that even non-continuous data is appropriately analyzed. So you can use yes/no data in ACM. There is no problem as long as you use the appropriate estimation method. ACM uses full latent or emergent variables, as I explained. So we are not using the mean value or the sum score. We are still using the whole set of variables or indicators. So compared to regression and correlation, when using the full latent variable, you get more valid results. I will show you an example for that. Okay, I got a question about the AVE and CR. What is your opinion about them? I will get to that soon, my friend. Okay, let's have a good example about comparing regression, typical regression, to regression inside ACM, but with full latent variable. So this slide demonstrates one of the key advantages of using ACM. On the left, we see a simple regression model where anxiety time 1 predicts anxiety time 3. Simple. This is a simple regression. 2 variables, one dependent, one independent, okay? In this case, usually we resort on the mean value, okay? We get the 5 indicators and shrink them into one mean value, sometimes the sum score. The regression coefficient here is 0.72. However, this approach doesn't account for potential measurement error in the observed scores because now the 5 indicators are shrinked. That is, we are shrinking the indicators into one, the mean value. With this, the reliability is gone or ignored. On the right, we have a full latent variable model where both anxiety time 1 and anxiety time 3 are modeled as latent variables with their indicators, the 5 items. We are maintaining the five items. Here, the relationship between the latent variables is 0.91, is stronger, and let's say higher from 0.72 to 0.81. The difference in effect size is notable. Why does that happen? The reason is that when we are using full latent specification, we control for measurement error. So ensuring the construct reliability is maintained. So we have that reliability. We are not losing it. This leads to an accurate estimation of the relationship between variables. In contrast, the observable indicator in the regression model assumes perfect reliability because it's now one indicator. Okay, so that's why the relationship will be lower in regression models compared to full latent structure equation modeling. So this example highlights a major strength of ACM, its ability to account for measurement error, which means that we are maintaining the reliability. Okay, what does full refer to in full latent variable? I'm referring to using the set of the items. So we are not using one mean value. So we are using the 5 items, as you can see on the left, on the right. I'm getting a question in the chat. So I'm trying to explain that. What does full mean here? Meaning that we have the items. We are not averaging them. So we have the 5 columns out there. Oh, I hope that's clear now. So the second remark, let's discuss this second remark and see how it can update our knowledge. ACM increases the validity of the results compared to the same task used in first generation analysis. So if you happen to be in a case where you have options to use regression or ACM, even for simple tasks, ACM can provide you with a more valid results. Isn't it cool? Okay. Although ACM provided usefulness to the first generation analysis, it is designed actually to deal with more interesting and complex tasks. Let's see some exciting applications. Okay. So let's go back to our previous multiple regression analysis example just mentioned, and let's test the hypothesis that vocabulary level test time 1 effect on VLT time 3 is indirect through VLT time 2. So from this is the regression model to this. Now we have something called indirect effect. We want to examine whether the effect of VLT time 1 on VLT time 3 is indirect through VLT time 2. So we want to see if the effect go through time 2, not direct. Okay. This involves adding a mediator. So VLT time 2 here, this is a mediator now, VLT time 2. On the left, we see that initial model where VLT time 1 has a direct effect on VLT time 3. The effect is 0.16 and the p-value is 0.08. So it's not significantly, it's not statistically significant on the left. This suggests that there is no predictive rule of VLT time 1 on VLT time 3, which is a bit weird, right? How vocabulary level test at time 1 cannot predict cannot predict scores on time 3. On the right, instead, we have a different specification. We see the extended model by introducing VLT time 2 as a mediator. We can decompose the total effect of VLT time 1 on VLT time 3 into direct plus indirect effects. So in this model, the direct effect remains non-significant. The B value is not the P, the B, the regression or the beta is 0.16 and is still non-significant, as you can see here. So it's still non-significant. However, the indirect effect, so VLT time 1 on 2 and then 2 on 3, this is called indirect. Okay, so this is the indirect effect is significant. So the indirect effect is significant. So this specific finding is super exciting. It shows or supports the hypothesis that VLT time 1 influences time 3 indirectly through VLT time 2. Okay, it means that the effect is not direct. It goes through time 2, which is meaningful and logic. The effects of students' scores on the vocabulary level test go through time 2 and then time 2 to time 3. It's not direct. We need to understand what happens on the middle. So this is the mediation. So this example shows how SEM allows us to go beyond simple regression by testing complex hypotheses about mediation or indirect effects. It provides deeper insight into the mechanism underlying the relationship. I think this is a cool feature of ACM. Oh, sorry. So ACM can improve the specification of first generation analysis into a more meaningful one, like the relationship between vocabulary level test at time 1, time 2, time 3, assuming that the relationship is indirect. This cannot be done in regression analysis. So this understanding should refute the claim that ACM is only for complex and advanced tasks. It is sometimes the appropriate method to test the relationship. So to understand how VLT time 1 related to time 3 goes indirectly through time 2. This is the meaningful, and this is the appropriate understanding of the relationship between the variables. Regression cannot do that, right? Okay. Do you know that you can run others' ACM model without data? Yeah, this is so interesting aspect of ACM. If the authors of the paper provide the correlation or covariance matrix plus the sample size, we can use this information to run the model ourselves. Isn't it fascinating? So using the correlation matrix like this one, you can actually run a model. You can take the correlation matrix to the ACM software, and then you can build your model, any correlation table from any studies, plus the sample size. You can replicate that model. And actually, you can try a different setup from the same paper using your idea. So, okay, how about changing these two and replacing the order of the variables? Yes, you can do that in almost all software packages, including Amos. So it's a powerful tool to replicate and relearning others' models. So ACM can replicate and respecify models by using the correlation matrix plus the sample size. And this is all what you need. It's really interesting. And I still remember that one of my papers was reviewed by an expert in ACM who replicated my model and told me in the review that I couldn't come with the same model you had. Can you please check your setup, or maybe you did something wrong? And he was correct. Actually, I missed something in the model. There was a correlation between two variables that I missed to include. So thanks to trying to replicating my model, that saved me a lot because the results were quite different without that correlation. So yeah, you can review others' work and replicate them actually. So how should we start using ACM? Let's talk about the guidelines, okay? We learned about the interesting aspect of ACM. So there are some guidelines to help you get started with ACM. Let's now focus on the composite model, okay? The composite model as shown on the left. These guidelines are based on our paper published last year, like 6 days ago, 2014, 24, sorry, oh, it's 14. Okay, so we published a paper about using CCA, the composite confirmatory analysis. Also, you can refer to Hensler. He published a fantastic book called Composite-Based Structure Question Modeling, 2021. So first, check the model fit indices. If you are dealing with composite, then please check the RMCA, SRMR, RMS theta, these three. Check these three. Make sure that the values for RMCEA, SRMR are below 0.08 for these two. And for RMS theta, the value should be below 0.12. These are the guidelines from Hensler, which was then adopted in our paper in 2024. Then, if the model fit indices are okay, then you can jump to the next step. So please don't go immediately to step 2. Start with step 1. Your model fit indices should be okay. Go to the next step, check the weights, not factor loading. In the composite, we have weights, not factor loading, because the direction of the relationship is reversed. So the items form the factor or form the composite. So in this way, there is something called weights. Factor loading, the factor loadings are based on the correlation. And here we are not estimating the correlation. We are estimating regression. So we are focusing on the weights. What do we need? We need them to be positive and significant. There is no specific value. Usually the weights will be very low. The weights will be very low, like 0.10, 0.25, something like that. Totally okay. It just shows how each item contributes, for how much contribution we have from that specific item. So the weight needs to be positive and significant. The p-value needs to be below 0.05. After that, if the weight is not positive, we can check the factor loading as a compromise. So this step ensures that the item still contributes meaningfully to the composite. Number 4, do not rely on Crambo alpha or average variance extracted, the AVE. Do not rely on these two. Why? These measures of reliability do not apply to composite models because they are based on correlation. In composite, we are not using correlation, we are using regression. So instead of these, focus on step 1, 2, and 3. There is a missing step here. I'm sorry for missing that. You need to check the VIF, which is more or less estimate the correlation between the items. We need the items to be as low as possible, okay? You can check more about this using the references above. In Jamovi, if you are using Jamovi and you want to estimate the composite, you need to do what is called the HO specification on the right. If you are using software packages like Smart PLS or Adanko or even GSCA Pro, these 3 software packages are based on composite. So you can estimate the model as you can see it. You can draw the items, you can specify the items and the composite. But if you are using the Jamovi, you need to apply specific configuration as shown on the right. We explained that on the paper, so you can go there and check more details. If you have a common factor model or a latent variable, the old friend, the old one, the older brother, you can use the guidelines, the golden guidelines by Hu and Pintler, 1999. You start with model fit indices like the RMCA, SRMR, TLI, CFI. And for the first 2, you need the value below 0.08. For the second 2, TLI, CFI, you need a value of above 0.95, at least above 0.90, at least. But if you get a value of 0.95, then you have a really good model. So you should be happy about that. The relationship are quite true. Then check the factor loading. Ideally, they should be 0.70 or at least 0.50. Then check the discriminant validity. Different ways, but here is a simple rule. If the correlation between the factors are above 0.70, then you are in danger of there is a threat to the discriminant validity. And if the correlation is above 0.80, then you should refrain from continuing the assessment, because when 2 factors correlated at 0.80, they are so similar. The variance shared is so high, probably more than 0.70 or 68% of variance is shared. That's a lot. So when you take these 2 factors into a structural model, how factor 1 and factor 2 predict an outcome, one of them will fail to predict the outcome because they are too similar. So one of them will survive and the other one will fail. Why? Because they are very similar. So it's really important to ensure that there is discriminant validity. 4, check the Crambo alpha, omega coefficient, and AVE. For the first 2, you need a value above 0.70, but less than 0.90. Yeah, maybe this is a new one. Try not to get a value above 0.90, because that means that you have lots of redundant items if you get 0.90. Usually people get this value 0.95, 92 when they have a lot of items, like 15 items measuring one factor. That's a lot. That's a lot. My recommendation is to use 3 to 7 items for each factor. This is my recommendation based on my experience and the guidelines in the field. So try not to go beyond 7. You are recommended to use or consider exploratory structural equation modeling, ECM. You can check our paper published in 2022. You can see the CFA on the left and ECM on the right. I can't go into details for these two. I have to move on, but I will show you the reference in the last page, or the last slide. So, remark number 5. ECM is an excellent method to test the validity of your construct. So if you want to check the validity of your constructs, whether they are emergent or latent, then you have the excellent statistical method. If you have an emergent variable, use the composite model, specifically the CCA, confirmatory composite analysis. If you have a common factor model, a latent variable, then you should use CFA, confirmatory factor analysis, or possibly, which is better, have been proven to be a better method, ECM. Okay. I'm not sure if we should go to some advanced topics like latent growth curve modeling or using ECM in experimental data. How much time we have, Maki, or guys?
Maki,
We have, yes, Giuseppe?
go on.
Yes, Giuseppe, go ahead. Go ahead.
So we have time until 2:30, but we would like to spend at least 15 minutes for questions.
Okay. So let's jump into the last. Okay, I will go to the most important ones quickly. So actually, you can do something like latent growth curve modeling to study the trajectory of a variable over time. Like, is there a growth of that variable? Let's see the vocabulary level test as shown here, VLT time 1, time 2, time 3, and how the growth is related to the initial level. This is a fantastic method within ECM. You can consider that. We published actually a paper using this method in applied psycholinguistics, and we wanted to see the second language reading growth in the students over 3 years, okay? Year 1, year 2, year 3. And here we included something called covariates. Here we have first language reading, second language aptitude, and anxiety. So we wanted to see which one of these 3 determine or affect the growth of reading achievement over 3 years. Fantastic, right? So exciting. What we found is that second language anxiety predicted time 1, the first year. So students who have high level of anxiety have high levels of low level of reading achievement at time 1 when they begun to start learning second language. However, anxiety didn't predict the growth of the students over the 3 years. What really predicted students' growth over the 3 years were first language reading achievement and second language aptitude. So these 2 predicted how good students will be over the years, not second language anxiety. We came up with some good interesting findings for the field by focusing on language-related skills not on anxiety, to understand how students grow. Thanks to latent growth curve modeling, it allowed us to study such an interesting topic. You can do the opposite, actually. You can see how the initial level and the growth of a factor predicts something in the future, something really interesting. For example, let's say not the one shown here, how the second language reading growth predict well-being, for example. So how the growth over the 3 years predicts well-being or happiness or something like that. This is really fantastic. Latent growth curve modeling can do that. And we published a paper last year using this technique. So it's the opposite. It's how the growth predicts an outcome, not as a covariate like in the last slide. So ACM provide greater information than first generation analysis. Not fancy results, but crucial one. This is my opinion. You can use ACM for experimental data. I can't go with that, but it's really fantastic. I need to give this example because it's really interesting. Let's say that you have two groups. One group uses, for example, WhatsApp with their teacher, and you want to see how using this mobile phone messaging can relate to students' motivation, achievement, and language anxiety. But you have a hypothesis that, well, using this WhatsApp, this application, doesn't directly relate to lowering students' anxiety. That should be indirectly through achievement, meaning that, okay, students use WhatsApp with their teacher, so their achievement increases, and then their anxiety decreases. So there is an indirect relationship in the experiment. So this leads to this, and this in turn lead to that. You see the setup here. We can see that this is the grouping variable, the experiment leading to autonomous motivation, motivation leading to achievement, and then to language anxiety. There is no direct relationship between using WhatsApp to anxiety. The relationship is indirect, which makes sense. Using WhatsApp with a teacher doesn't immediately reduces the students' anxiety. They need to have more motivation, more achievement, and then their anxiety decreases. No statistical methods can answer such a question, but structured question modeling. This is really fantastic. If you want to learn about the sample size, this question, you can refer to the barcode. Please take a picture of that. Specify your model on that web page, and it will tell you how large sample size you need to achieve statistical significance. So here is a small thing, the bottom line. The more relationships you have, the more or the larger sample size you need. The smaller your model, the less sample size you need. This is a general guideline. Okay, if you have a simple model, maybe you can achieve significance with 120 sample size. But if you have a larger model, then larger sample sizes. But you can use this one to have the exact minimum sample size. ACM can be an excellent method for experiment. I know some applications of ACM can be difficult to understand. Hopefully, I did my best to explain them in a simple language, but please do not look around or reject papers if you are a reviewer or editors, because I suffer a lot of that. Ask, learn, and have a positive attitude. These are the references, some of the references I used in this topic. And with that, I would like to thank everyone attended this talk. Thank you, everyone. If you have questions, then the floor is yours.
Thank you, Abdullah. That was so clear and so interesting. Thank you. I guess we have many questions. We have 20 minutes for questions.
Okay.
We have one question from Sama. What if I'm studying perceptions of the students after conducting an intervention? Some variables are latent and other are not.
What if I'm studying perceptions of the sense after conducting an intervention? So I think this is part one of the question. Some variables are latent, other are not. I didn't get the purpose of this question. I feel like I have two things. About latent variables.
Sorry, may I speak
Yes,
out? Okay, thank you so much. First of all, I would like to thank you so much, Prof. Abdullah, and also those, I mean, the moderators and those, the committee are behind this amazing and insightful workshop. I've been waiting for this since almost, like, say, 2 months. I mean, not 2 months actually, since you have already, since you have already published that in your Facebook. So yes, let's say that I'm a novice researcher. I've finished my PhD. I'm also working in quantitative analysis. But I've never done I mean, structural cohesion modeling before. So currently I'm working on a paper that is about I'm using confirmatory factor analysis. This is actually, I'm doing that because I'm having a questionnaire after conducting an experimental, a quasi-experimental study. So here, like, based on the items of the questionnaires, I'm having different items, and some are related to motivation, some are related to the perceived acceptance of the interventions that have been done, and some are related itself to their own perceptions towards them. The treatment itself that was conducted for the experimental group. So I'm asking them whether they're positive about it or not positive about it. It depends on their own perceptions. So when I already designed the model and everything, then I find that I have to make a direct path analysis. Relation from the, let's say, not from the items of the question, but from the observed variable itself. Like, I didn't get it, to be honest, but I didn't get a very, let's say, a significant result out of it at the end, although I could see when I have done just let's say as a basic analysis, like let's say t-test or on ANOVA, the results were actually significant. But when I used the Amos, using it wasn't significant. That's why I'm a bit confused about that. I hope I got my question clear.
Okay, there are several reasons why would you get different results from like a species and then Amos. For example, Amos by default handles missing data using the full information maximum likelihood. So in this case, you will get different results because now the software using all the information available to estimate the missing data. This absolutely results in different path coefficients or regression. So this could be one reason. The possibilities or reasons can vary, but this thing can be one expected result or expected reason why you get different results. So yeah.
Okay, so just another question. Can we have, let's say, if that we are assuming let's say a correlation between, let's say, the variables, let's say the observed, not the latent variables themselves, but within one is actually affecting the other one among them. Can we also, is it correct to say like that, or to have a model like that?
It's either correlation or regression. It's not
it cannot be both. I see.
No. Actually, but here is the thing. If they are two variables, latent variables, then correlation or regression will give you the same results.
I see. Yeah. Okay. I got it.
Yeah, you will get the same results because you only have two constructs and one estimation. So regression or correlation will give the same.
Although at some points we can have moderating and also mediation variables in SEM, like, right?
Yeah, that's right. I explained that in the slides. You can always use mediation, which is one of the advantages of using SEM. So that's right.
Okay. Thank you so much, Prof. Thank you.
You're welcome. You're welcome.
Giuseppe, there is a question by Michael Paradowski, who asked which one should be reported. Is it the R squared or adjusted R squared? An interesting question.
There is a debate about that, but typically in structural equation modeling, we get the R squared, not the adjusted one, but you can always report the adjusted one. What I think or read somewhere, not sure what is the reference, it was years ago, that if you are conducting an experiment, then you should report the adjusted R square. But usually the adjusted R square is more favorable. It's favored because it adjusted for I think it's adjusted for the error. So, but usually the difference will be very minor, very minor. So yeah, if it's, for example, 0.81, the adjusted one will be 0.80, something like that. So it's not a huge difference. But if you want to use the adjusted R2, then you are in the safe track. No one will blame you.
Thank you. We also have a question from Bianca. For very small samples, let's say 12 participants with SPSS, we normally no parametric analysis. Can we do SEM in this case?
12 cases. With 12 cases, did I hear that correctly?
That's what I read. Bianca, do you want? Yeah.
Yeah, 12 participants, yeah.
12. I don't think 12 would be feasible in any application of SEM. It's really in any statistical model, actually, because we rely on the p-value to see how significant is the relationship between variables. But unfortunately, with this very low sample size, I'm not sure if any statistical analysis would be helpful in this case. This is at the heart of statistics. Large sample sizes. Always try to be hungry.
Thank you. Archie, do you have a question?
I will be glad to ask a question. Nice to see you and thank you for your lecture today. It's been a couple of months since we last met in Kuala Lumpur. Time flies.
That's right.
I probably have similar question to what I asked you last time, but we didn't have much time to talk. So when it comes to the analysis of formative or emergent scales in general, to what extent the process differs from the analysis of latent variables? I mean, of course, the direction of arrows is different, but when it comes to Jamovi tutorials or actual process, can you elaborate a little bit on that part, if possible? Thank you.
Oh, okay. So I think I mentioned that somewhere here. Yeah. Okay. So Jamovi is a latent variable software package. Basically, it's developed to estimate latent variables or common factor models. So to allow or to let Jamovi or any other SEM packages to accommodate emergent variables, we need to use a specification called HO specification. It's like going around, it's like fixing the model so it can make this one on the left possible to be estimated in Jamovi. We showed an extensive example in our paper. You can follow the steps. You can actually copy the code in R, just copy and paste. You will get that one. But I think it's a bit out of the scope of this presentation to show you step by step. But please, let's have this in person, and I can show you how to specify emergent variables in Jamovi or CHASP or whatever. But I think it's beyond. This.
Of course. I just needed some basic.
Was this your question?
Yes, perfect. I'm gonna play with Jamovi with this part because I was quite interested for a long time in formative, or as you call it, emergent variables. But there is a lack of information when it comes to formative constructs. When it comes to R or Jamovi, it's usually connected to M plus. At least that's what I just discovered in different forums. For example, it's impossible to find any information in Google forum of Lavan, for example. It's not in there when it comes to formative constructs. But that's why I needed this question. Anyways, I will give floor to others. I will probably DM you and we can talk more. Thank you.
Yeah, please. So in simple, M plus, Jamovi, Jamovi, JASP, all of these actually developed to work with common factors like this one. If we want to use composites, we need to go around and do a small modifications like on the right hand. So this is a simple answer to this. Thank you. Any other question from our friends?
We have a question from Mingling. For 110 participants, can we do latent growth modeling curve?
This is really tough. From my experience, when I tried the power analysis, which I showed on which page? Yes, this one. So please use that one and check for yourself. But from my experience, my personal experience, you will need something above 150 to get significant results. It also depends on how many variables you have in the latent growth curve model. If it's simple growth, you could have like between 100, 150. It's rough. So give it a try. Try this package or this website and see. Well, in this website, you tell the package or the window your specification and the anticipated effect size. If you anticipate that the effect size will be 0.20, and so when you click analyze, the software will tell you if you can get significant result by your sample size. If we set 110 and you are thinking that the effect will be 0.20, would that be a significant? So he will the software will calculate that and work out for you and tell you if you will get a significant result, or maybe you need to increase that to 160 or 200 sample size. I don't know. I cannot answer that just straight away. So please try this useful website.
Thank you. Thank you, Doctor. And because this data, previously I collected this data from the experimental participants, the group and the control group. So all of the total sample size is almost 110 participants. But I would like to conduct this because I have already collected the data from across the 3 stages. Yeah, across the 3 stages. So I would like to try the latent growth modeling curve. If it cannot present a significant result, so maybe I would like to try to use
why not?
SEM
Try it.
Yeah, try it. Yeah, I would like to try, but
go ahead.
I think
no one
I
can stop you. No one
it.
can stop you. Go ahead and try it. I thought that you were anticipating 110. In this case, you can try the power analysis before collecting the data. But since you have this data, I hope you do not remove any of these 110 because you can handle the missing data using the full information maximum likelihood, which is fantastic compared to ANOVA. So give it a try. See if you get a significant effect size. Your setup, since you are doing an experiment, your setup should be like this one. You should have like this one. You want to see if of the growth on something like motivation is only among the experimental group. In this case, for example, we have a significant effect on the slope for the experimental group, on the slope or growth. It means that only the experiment group showed an increase on the growth on vocabulary level test. That was an experiment, by the way.
Yeah, thank you. And by the way, if I conducted this latent growth modeling curve, this one to conduct the experimental group and the control group, so shall I to create the two models to compare them, or to create two models?
You can use the same setup as you can see it in this slide.
So what I mean is that so because in this study, if I conduct this some intervention conducted in the participants, and then I have already collected data from the experimental group and the control group. So I would like to, so shall I need to establish two models to compare the experimental group's situation and the control group? For example, these variables that are related to the motivation, anxiety, enjoyment, and work engagement.
Okay, I see. So you should analyze models for each variable. So for motivation, you should analyze the data for motivation, for, let's say, for self-efficacy and for enjoyment, like this. So yeah, you should have different models in this case.
So for example, that means I got it. So for example, if I want to compare
same setup as you see now for each variable. So for example, in my case, let's say I'm doing an experiment testing how the experiment increase students' vocabulary test and increase their motivation. I will have two models like this one for motivation and one for vocabulary knowledge. You could do one large model including both motivation and vocabulary test, but you should have larger sample size because the model is now large.
Because there are lots of items.
Exactly. Yes. Or let's say parameters, lots of parameters. So you'll have 2 intercepts, 2 growth, and 6 variables. So you need larger sample size. The compromise for this is to split. So have one model for, in my case, vocabulary test, and one for motivation. So this is a good idea.
Got it. Thank you so much.
We are running out of time, so maybe the other participants who would like to ask questions could directly send you an email, since we only have 2 minutes. So unless you want to very briefly answer one of them.
Okay, I will write my email in the chat, so please go ahead if you want to contact me. You are more than welcome. I have a question here from Michael. Doesn't FIML or full information maximum likelihood estimation assume your data are missing at random? That's correct. Then if the missingness is systematic, it may yield misleading results. I agree. That's right. This is something that cannot be handled by statistical modeling or any missing data imputations. If there is something, if there is a missing over time, that is systematic. Let's say, for example, those who are old refrain from responding to a specific question. Full information maximum likelihood cannot help. That's right. So we are assuming that the missing data at random, it's just random, not systematic. So it's not, for example, all people in the questionnaire intentionally ignoring to answer a specific question. In that case, you need to treat that differently. It's not something that analysis can handle. Yeah. Thank you for this good question.
Thank you. Thank you so much. Please, everybody, join me in thanking Professor Abdullah ALAMER. It has been a really great and inspiring and very interesting talk. So thank you on behalf of the whole Research Method SIG. Thank you so much.
You are welcome, and I hope I really enjoyed the talk, and I hope everyone here enjoyed it as well. Let me know if you have any feedback, questions through email, and let's dream about ACM tonight.
Thank you, ALAMER.
Thank you
And
so
of
much.
its beauty, as you say, it's so interesting that you describe such a difficult topic with words like beauty, appealing. Thank you.
Much
Thank you.
appreciated.
I think you've managed to make us be really interested in this. The only problem we have is the sample,
Yeah,
but we'll do our best.
Happy to learn that. Please do not reject papers if you act as a reviewer or an editor.
Thank
Okay,
you so
thank you
much.
so much.
Thank you.
Thank you so much. Thank you.
Well.